Hello everyone. Let's have a brief look on chapter 9 about morphological image processing. These are important tools, very classic tools in image processing that are very useful. Last year I just dropped this topic off because I thought they are so classical that would be useless to talk about it. But then I realized in the middle of the projects that the students actually needed to use some of these. So this is like not teaching you calculus just because it's too basic, right? So let's have a give a brief look through it, and maybe I'll take 1 hour or so. I won't stop as usual. Now I believe that you are all grown-ups, that you can easily stop the reproduction at any time, have a break and return it. Okay, so morphological image processing. The idea is to use mathematical morphology to extract some image features or image components. And there are a number, the idea is very basic. And very powerful because we can compose and combine these morphological operators on a number of algorithms to extract boundaries, skeletons, and even to construct the convex hulls of sets of points. So far, we've been playing with a linear algebra, with matrix manipulations and matrix operators. We've played a little bit with a calculus, with the gradients, Laplacians, and so forth. This chapter we're going to play with mathematical morphology. Basically, that uses notions from set theory. Let me get a pointer here. From set theory. So our images now are going to be understood as sets of points, sets of pixels. If you're working with binary images, the only thing you'll need is the x and y coordinates of the pixels. Obviously, with grayscale images, you need, besides the spatial position, also the intensity value. So we're going to be playing with the sets will be defined on the sets of integer numbers, three-dimensional integer numbers. All right. So before we introduce morphological operators, we have to understand that in this area we understand two types of sets of pixels. One type is objects. Objects are regions in the image that we see, or that we don't see, depending on the kinds of images and the kinds of spectrum that you're dealing with, and the structuring elements. So this is the essential idea of this area, is the idea of the structuring elements. Objects are sets of foreground pixels, as I said, regions in the image. Structuring elements are specified in terms of foreground and background pixels, plus what we call don't care elements. They are denoted by a small x, as we're going to see in a minute. And these structuring elements we used in a kind of similar way that we use convolutional kernels, but they are not convolutional operations. So we are going to sweep the matrix representing the image, with these structuring elements, and we're going to apply some sort of transformation given defined by these structuring elements. So, that's the analogy stops there. So it's not we're not doing the convolutional operators. We're not turning the kernel 90 degrees, and we're not doing a convolutional operation of its multiplication, sum of multiplications, anything. But we have to take into account the padding and sliding operations. So they are the same. All right. So we have objects then represented as sets, and the structuring element also represented as sets. Of course, we're dealing with digital images, so these objects are then objects defined in a digital way, and also the structuring elements is a digital structuring element. One basic idea that we're going to be using throughout is the reflection of a set of a structuring element B about its origin. So if B is the reflected structuring element, it's every element W that composes B, so that W is the negation of B. So now if B is the element X and Y, then the B reflected will be minus X and minus I. This will be easier to see in the examples. It's a little bit difficult to understand from here, but basically what we're doing is if we have an object like this, if we apply this operation on this structuring element, then we're going to have an object that's this, right? The reflected image of the object. In translation is the same thing that we called strides in convolution. So we translate the structuring element a certain number of steps. Or translate or slide the structuring element over the image, and at each location of the image, each location that this structuring element is overlapping with the image, then we do a set operation. So that's why it's not a convolution, because we're not doing the sum of multiplications, but we're doing a set operation between the structuring element and the area of the image immediately under it. Now, just to have a kind of basic idea, if this is the image, and then what we do sliding is we pass the structuring element translate it over the image, over the entire image, and do depending on the definition of the operation, we do a set operation on top of it. So this is the general understanding. Let's see how it actually works. So structuring elements can be any sort of feature, pixel-like features. So this, for instance, is a structuring element. It's one structuring element. This is its reflection. This can be another structuring. In this element, these are all pixel. These are all pixels. Let's say foreground pixels, right? In this structuring element, and also in its translated form, you see that they are absolutely identical. That's because if we flip this image through, it becomes the same. So this is a foreground pixel and this is a background pixel. All right. The same thing with this guy. So these are foreground pixels. These grays, these shaded areas, colored areas are foreground, and this is a background pixel, background element in the image. This is its inverted form. And this, for instance, you have here it's foreground pixels, background pixels, and this is no care pixels. We're gonna see what doesn't matter means when we start operating them. All right. So you can have any sort of sizes and shapes. So for instance, we can have big structuring elements or very small structuring elements with just one pixel. So this is all possible. Now, a very basic morphological operation. So if we have an image I, that's this image here on the left-hand side, with a foreground object, which is this kind of bone-like shaped object in the middle, or it can be an H. And this is actually foreground pixels in the image, right? And these are background pixels, which are pixels in the background of the image. This is the structuring element. So the operation, the morphological operation then, for a new, the morphological operation what would slide over this structuring element. We slide it through the image. Slide means just moving the structuring element on top of this image, right? And at each increment of the translation, if B, the structuring element, is completely contained in A is the foreground object, this is A, right? If B is completely contained in A, we mark the location of B as foreground in the new image. Otherwise, leave it as background point. So this is the operation called erosion. Erosion. So what's happening here is the following. So I'm gonna get this structuring element, pass it over the image. So is the structuring element B totally contained in the foreground image? No, because this part is outside, this part is outside, this part is outside. So it will be the same thing for every step here. So what do we do with the in these pixels in the image that I'm constructing? Just leave them blank. Just leave them blank. So don't filling up anything. Now, in the case that the structuring element is totally contained. Oops, the structuring element says 1, 2, 3, 4, 5, 6, 7. It's a 3 by 3 matrix, so I'm drawing it wrong. Sorry about it. So if this element is totally contained in the image, like in this case, then the middle where the dot is, which is the center of the structuring element, and the center could have been defined at any point, at any point in the structuring element. Then I mark the region in the constructed image. I mark the pixel as foreground object. So this is the result. This image is the result of passing this structuring element over this image and eroding it. Eroding is this operation that you just saw, and the definition, there is a symbol for erosion. The symbol is this kind of a minus with a circumscribed by a minus circumscribed, right? There is every z. So the result of the erosion is every z, so such that z is the center of the structuring element B if it is totally contained in the foreground image A. All right, this is exactly what we did here. When B is totally contained in the image A, where I collect the center of this B and mark them in the resulting image as a foreground object. Everything else will be background object, because in these cases the structuring element wouldn't be totally inside of the foreground object. All right. Of course, I have to take into account. Also the background. So in this case, I didn't need to take into account the background pixels because the structuring element was totally composed of foreground pixels. Now, if the structuring element also has background pixels like these ones, I'll have to take that into account. So still, I have to make certain that the whole thing is inside of the image. What does it mean inside of the image? It means that these pixels that are foreground pixels in the structuring element will match foreground pixels in the original image, and these pixels that are marked as background images will have to match background pixels in the original image. All right, so when I have a don't care pixel, this could be either background or foreground. I really don't care what kind of pixel is this one. That's what kind of pixel in the image this one is related to. All right. Okay. So, and this is the longer definition. The definition is then when I have this kind of cases here where I have to take into account background pixels in foreground as well as foreground pixels, and I have to take into account not only the image A, but also the complement of the image A. And you know from your set theory knowledge that the complement of the image A is everything is background, right? So the complements, if A is the image, its complement is the background pixels. All right. So this is all what I said. Now, there are a number of examples here for erosion. And obviously the erosion depends totally on the structuring element. If I have a structuring element that is a square of this size, and I pass this square over the image, what I have is like an eroded square. Pass this little square as a structuring element for erosion on this bigger square here. What I have is an eroded image without a portion here, and this portion is exactly of the size of this little square here, right? And if I have a structuring element that is this rectangle, when I pass this rectangle through this image, it has this the longest size is D, so the longest size is D. It is exactly of the height of the original image, so I'll only be collecting this point. So the resulting of eroding this square, this original image here by this structuring element will be just a single line. Just the very center of this image will be the result of the erosion in this case. All right. So there's a number of examples, interesting examples about erosion on the internet. Let's see one of them. I think this one. So this is the structuring element, this kind of reddish element. This is the image, the foreground image, and the black pixels here are the background image. And this is the output image, right? So I'm going to create the output image given the sweep over this structuring element over this picture. Now let's see how it goes. Right, filling up with nothing because it's not totally inside. Now it's totally inside, and you see that whenever it's totally inside, on this side you're seeing that the image is being created. When it's not totally inside, I just fill up with nothing, with background pixels. All right, did you understand it now? It's very simple idea, and the funny thing is that the simplest ideas are the most difficult to explain because they are so simple that really. Let me try to stop it at the very end so that you can see that the resulting of this erosion process, given this particular structuring element, is a kind of eroded copy of this object. What I mean by eroded copy is that it's a shortened version of this object, right? When this object has 1, 2, 3, 4, 5, 6, 7, 8 squares sides and its height, the resulting has 1, 2, 3, 4, 5, 6. All right, is that clear? Let's see an erosion by a more interesting object, such as this one. It's the same thing, but I have a lot more an object that's a lot more complex, and also a structuring element that's more complex than the other one. So the structuring element is this red thing, this red diagonal. It's eroding the entire image and only returning a few of the regions where the structuring element entirely matches with the foreground object. Alrighty, let's move on. So why do we need erosion? So we can use erosion to remove some image components. So imagine that I have this kind of X-ray of a microchip, and I'm not really interested in these connections. I'm only interested in the microchip right at the middle. So I just pass erosion with an appropriate structuring element to get these results. Now depends on the sizes of the structuring element. In this case, they use a square structuring element like the one you've seen in the first example. And in the first case, we use an 11 by 11 structuring element. So we started from this image and end up on that image with an 11 by 11. Now, if we pass a 15 by 15, we start from this image and end up with this image. And if we pass a structuring element of 14 by 45 by 45, then we are going to start from this one. This will be the original image, and this will be translated or eroded into this image here. All right. So in the same sense that I can do erosion, I can do dilation. Dilation is the inverse operation as erosion, and it has the obvious sign of a plus, where erosion is a kind of circumscribed minus. Dilation is a circumscribed plus. So I'm going to collect every center of the structuring element such that the intersection with the foreground pixels is not empty. Right? Unlike erosion, which is a shrinking or thinning operation, dilation grows or thickens objects in a binary image, always with respect to the structuring element. Now, using the same structuring elements as the other example that we eroded, and remember that in the end I had just the center, a straight line passing through the center of the original element. If I am dilating this element here by this structuring element, what I have is like a fatter square. So this is the original square, and now we see that it's actually grew on both sides. Now the same thing if I pass this kind of structuring element, then what I'm gonna have is, as a result of dilation, is this elongated, from a perfect square, what I end up having is a rectangle by passing a dilation. There's also a great example from Peter Cork. Peter Cork is a very famous robotic scientist. He has a very good book on robotics, and also his great applets showing this kind of stuff. So this is the result of dilation. So whenever there is an intersection, I just build up the element on the output image. So see, there is not only even if there is only a single pixel as intersecting with the structuring element, I create the other image on the others. Create the output. See, I put a foreground point at the center of the structuring element with respect to the output image. All right. Okay, so these are the basic ideas. Now, the application of dilation is used to reconstruct pieces, missing bits, such as, for instance, if you use a bad scanner where you have this kind of undefined letters, if you use dilation, we can get a better representation, a better depiction of these letters just by fattening them up a bit. All right. You probably have guessed already, erosion and dilation are duals of each other's with respect to complementation and reflection. So this means that A eroded by B, the complement of this is the complement of A dilated by the reflection of B, and the same thing for the dilation. A dilated by B, the complement of this operation is the complement of A eroded by the reflection of B. This has this has more mathematical interest, and we can use these properties to prove a number of theorems related to morphological image processing, and also to prove the correctness of our algorithms. If you are keen on learning the mathematics, then you're free to dig into all of these definitions. Mathematical morphology is a huge field, and people do a lot of interesting things with that. But if you are an engineer, you don't really need to bother about the definition. Just need to bother that one, like plus and minus in arithmetics, erosion and dilation are duals. Right? Now, I'm assuming that you understood erosion and dilation. This is all there is to understand in mathematical morphology. Now, what we're going to do now, and you can investigate it throughout the rest of your career, is that we can combine erosion and dilations in a number of smart ways, not only creating algorithms, but also creating new operators, new morphological operators. And that's what something is very cool. That's a mathematical morphology and morphological operators are very elegant ways of manipulating images. Now, and these are the two most important and most used combined operations, which is opening, or I should have said operations that are defined on combinations of erosion and dilations. One of them is opening and the other one is closing. Now, the opening, let's read this. The opening of a set A by a structuring element B is the erosion of A by B followed by a dilation of the result by B. Intrinsically, this is the symbol for opening. It's a little empty ball. It's fine. It's fine to remember. It's a ball with nothing inside. So you're opening. So given let me start again. The opening of a image A by a structuring element B is the erosion of A by B, and then the opening of and then the dilation of the result of that by the same element. And same thing, closing is the dual of opening of a set. The closing of a set A by a structuring element B is the dilation of A by B followed by erosion. So opening, you first erode, then you dilate. Closing, you first dilate and then you erode. Now, opening, why do you use opening? If you want to smooth contours of objects, and also to break narrow isthmuses and to eliminate protrusions. Closing, on the other hand, tends to smooth sections of contours and fusing narrow breaks and long thin gulfs, eliminating small holes and filling gaps. Now, you can understand opening as by the union of all the translations of the structuring element B, so that B fits entirely in A. So given the initial image that is this A, this kind of V-shaped or upside down seat, right? Upside down box with a V shape in the middle, and this is the foreground, this is the background. Now, for the opening, the opening of this image by this structuring element is like if I capture all of the instances of this element, such that each instance falls inside of this foreground object, and this will be the result of the opening. You see why the opening? You have kind of, you opened this kind of, or this kind of narrow part of this image. So you basically created two distinct regions, two disconnected regions out of this from this initial image. Now, closing, as the name says, you can understand as closing as the complement of the union of all translations of B outside A. So if I just moved B around on the touching A and collect the I get the union of this and just collect the complement. The complement will be this part here, and you see this you're smoothing sharp edges. Whereas here I had the sharp edges, I had this smoothed out, and also you don't see here, should have been smoothed out, but at these corners here. All right, I don't think the figure you're gonna see in the exercises. We're gonna run these functions on with OpenCV. It's very easy to run these functions with OpenCV. Now, so let's see more examples of opening and closing. Let's start from this figure. This is the original figure. This is the structuring element. Now, the first thing, if you're gonna use opening, the first thing I do on this image is pass this structuring element and erode it. So this is the result of erosion A by B. I end up here. This is the erosion, and then I use B again to dilate these two parts here. I use B again to dilate these two parts here. What I get is then two separated parts. What happens is that this part here was cut, as you can see here. This is the result of the opening, but while also I smoothed the sharp edges. This is clear that this has been smoothed here, whereas before was very sharp. And also this kind of peaks here were smoothed out. And let me clean this, and then you can see it better. All right. Now these two images here, these two lines here are the results of opening. If we do closing is represented in these two lines here. So for closing, first I dilate the original image using the structuring element coming from this image here, and the result of dilating that will be this image here. And then from this image I erode it with the same structuring element, and the result is this thing. So this is the result of closing. What we see is that I still have the image, the two parts totally connected, but now if we look at the edges, they are, well, first this connection became slightly fatter, slightly larger, but also the edges are very smooth from here and here and here. These are always smooth edges now. Okay, so applications of openings and closings, traditional applications if you want to clean data. And we're going to do in the exercise to clean data. So for instance, for this fingerprint images, you have a very kind of noisy image here where you see some pepper, salt noise, not pepper, salt noise here. And if I just pass, I erode that with this structuring element, I basically clean most of this noise. But together with this noise, I also kind of lost information. If you look clearly here in the fingerprint lines, there's some of the lines are almost disappearing. See this corner here? Let me clean this so you can see it better. Then, well, I got rid of the noise, but also got rid of some information. And now in order to collect this information back again, I then dilate this, and then I have the fingerprint back again. All right. So, okay, so there are various other combinations of erosions and dilations resulting in a vast number of algorithms. I'll change gears here, and I'll just run through these algorithms. Maybe it'll take more 10 to 15 minutes to see that. If you need more details, please read the book. The book explains very well. And if you have any questions, always look for me, ask me questions, send me emails. So why I'm going to run through the algorithms, they don't really carry anything new in terms of morphological operators, because it's just a smart combinations of opening, closings, and dilations and erosions. All right, but there are a few new concepts. A few of the applications of these algorithms, I'm sure you're going to need at a certain point in your project. So let's see briefly the algorithms. One of them is this hit or miss transform. That's HMT, hit or miss transform. As you see, it's a smart combination of erosion, but here I have two structuring elements, B1 and B2. B1 and B2. One of the structuring elements, I'm gonna erode the foreground pixels of an image, and the other element, I'm gonna erode the complement. I'm gonna erode the background pixels. So we can see erosion actually, as we have to get the image, the structuring element totally inside of the object. We can kind of use it for detecting shapes, and that's the main idea behind hit or miss. We're actually trying to detect shapes not only on the foreground but also the same shape on the background. And what happens is that the final result is actually we can actually find the exact location of certain shapes using hit or miss algorithm. And I knew that some of your projects are related to finding shapes, and this is a good simple solution for you to try out and compare with more modern solutions. All right, so let's see, we have this image composed of three rectangles. A rectangle E, rectangle C, a rectangle D. And let's suppose that I want to find the location of only rectangle D. So the idea here is then you get the two structuring elements. They are exactly of the same size and shape as D, but with one of them I'm gonna erode with B1 I'm gonna erode the foreground pixels, the foreground objects, and with the other one I'm gonna erode the background objects, the complement of the background objects. Okay, let me clean this. And what I have, let's see, in the first step, by doing this process, so just by eroding A, which is A is the foreground objects, A is the union of C with D with E, just by eroding A with the structuring element B1, what I end up having is just this element and this dot here. Now let's get the background objects, or you can also see that now the background are these objects, and the foreground will be the old background, and I'm gonna use B2 to erode that. By using B2 to erode the background that's now turned into foreground, what I end up is with this object here. Right? Now, what is the definition of this HMT transform is that I'll get what? I'll get the intersection between eroding the object A with B1 and eroding the complement of object A with B2. And what's the intersection between this image and this image? This point. This point, which is exactly the origin of the object that I wanted to find. Wow, impressive. That's all there is. As I said, there's only dilation, erosion, and this is a smart combination of dilation and erosion. But now using two structuring elements, and also playing with foreground and background, which background is just the complement of the foreground, and that's it. There's nothing more to it. Now there's a whole bunch of other algorithms, so we can use again a smart formulation. Where is my pen? Oh, here it is. A smart formulation of erosion with actually erosion and subtraction here. Look, erosion and subtraction. By just doing erosion and subtraction of this image with this structuring element, what I found as a result is the boundary. So I found the boundary of this image here. This is unbelievable. This is unbelievable. Just the boundary. You see? This is I think I always get amazed by it, and it's extremely simple. That's just erosion and subtraction. And I found the boundary of an image. Erosion and subtraction by a very simple structuring element. And I can use, so for instance, that's was George Lincoln? No, it's Lincoln, right? Not George. Confused George Washington with yeah. So this is the shape of the mugshot of Lincoln. All right, whole filling. As I can, the same way that I can find a boundary by applying some smart operations here, I can fill up holes. In this case, what we're doing is a dilation. But that's a tricky here. It's an incremental dilation. So I'm going to generate a whole a sequence of images from image 1, 2, 3, 4 by dilating a single pixel that's part of the whole of an object. Let's think of a donut here. This is the oh, it's terrible to it. So this is a donut. You see that donut has a hole in the middle. So if I start from a pixel in the middle of this donut and dilate it by this by the structuring element, dilate this pixel at many steps. So you start from a pixel, dilate it, and get it bigger. Dilate it, get it bigger. But get the intersection with respect to the complement of the region of interest that I'm observing. Then what I get is a filling up this hole. So let's start from this image that's excuse me. So we start from this image that is the boundary of a number 1, and for this procedure we also need the complement of A, which is everything that's not foreground of the number 1. So this part. It starts from this structuring element, but that is a tricky. So I have an initialization. Someone has to give a pixel inside of the hole that I want to fill up. And the hole is all of this white part inside of this boundary, right? So I want to fill up this hole. So just by applying this simple set operation, and again I start from a single pixel, grow a single pixel, dilate it, and get the intersection with this image here. Which is the complement of the image itself, and then grow it a little bit more, and grow it a little bit more, and grow it a little bit more. Then I have what exactly? the inside filling up the whole of that. But if I want to fill up the hole, then I have to make the union of the hole, which is this part here, now that I found what the hole is, with the original image, which is this part here, right? I end up having, this is the result of filling up the hole. Let me clean this for you to see it properly. Right? Can you see that starting from this is the original image, and then at the end I have the image without the hole. Right? And we can destroy any donuts with that. So this is an image of a number of donuts. Right? And using hole filling algorithms, I got rid of, the result was no donuts. So I lost a donut. Right? It's because a donut is not a donut without a hole, right? That would be something else. The same procedure can be used, or similar analogous procedure can be used to, instead of filling up holes, to find the connected components. And that's the same operation, but instead of applying it with the intersection of with the complement of I just get intersection with respect to I. And the result again I have to start from a single pixel given at the edge, at the boundary that I want to find. And then I just grow applying this operation. I just grow this image so that in the end I have exactly the boundary that I was looking for. Now, one student once asked me, so why do I need a boundary? Didn't you have it originally? No, I just had pixels. I didn't have the actual locations of the boundaries, right? I just had pixels. Again, we know what the boundaries are because we are humans, we are smart. Computers are stupid. So they have to track or to walk through the boundary like we are doing here. Basically what's doing is walking through the boundary so that now I know exactly the coordinates of the boundaries of this object. Okay? And there are a number of applications. This is X-ray image of a chicken fillet with bone fragments. Yeah, I don't know what's the use for it. Oh, that's detection. Right, that's detection of foreign objects in packaged food. Yes, so in the food industry, in computer vision algorithms for the food industry, morphological operators are very important. Finally, finding the convex hull of sets of points. Convex hull, you know what, when a set of points in the Euclidean plane is convex, right? It is convex. Let's give it this region here. This region that's this region here, right? This object here. So this object is convex because for any points, 2 points inside of this object, a straight line will be totally inside of this object, right? Any 2 points inside of this object, a straight line will always fall inside of this object. This is a convex object. Now, this object here is non-convex because there are a number of points here that if I connect them by a line, this line doesn't fall inside of the object. Right? This line doesn't fall inside of the object. Now, why do I need this? That's because a representation of a non-convex object is very hard. It's very hard. And it's easier sometimes, most of the times, I want to detect obstacles. I don't need to detect, imagine detecting a shape of a weird kind of column that goes all around. What I want to get, I just need to get the convex hull of this object. The convex hull, and then represent it with a simple geometric object that I know the function, right? So what I want to create is the convex hull, and the convex hull of this object will be then just to close it up here. And I can, there's a number of algorithms for convex hulls, and the ones that use morphological operators, it's not the most efficient of them, but I decided to include this in this lecture because the idea of convex hull is very important. You're going to find it while developing your projects. Creating a convex hull with morphological operators, we're going to have to find 4 structuring elements, each one representing different sides. So this represents the right hand side of images. This represents the bottom side. This represents the left hand side. This represents the top side. All right, and then I apply what? I apply the hit and miss for every one of these structuring elements, and then get the union with the original image, right? Because I want to unify. I want to it's kind of filling up a hole, but I'm filling up a hole that is open-ended. So the procedure is that we're doing this kind of hit and miss, growing the region, and then obviously then I end up with this large region here, which is not the convex hull. The convex hull will be something like this, right? Something like this would be much shorter. So this is bigger than the convex hull. That's why this algorithm is not the most efficient one, because then later, after creating this object, this larger objects, and then I have to apply limiting growth. So I have to bound the growth of this object to get the good convex hull. So it's not the best solution. Thinning is another important thinning of a set A with the foreground pixels by structuring element B is given by, again, the hit and miss transform by a sequence of structuring elements. So so again I have to use a number of structuring elements. Each structuring element will be related to one particular feature of your foreground object. So this will be again the bottom, this will be the corner, this will be the side, this will be the top left, this will be the top, this will be the top right, and so on and so forth. And now what I do is a hit and miss algorithm. It's kind of eroding the object, but eroding with every single feature that it has until I get only a single connected component. You see that this is as what we call a skeleton of the object. And this skeletonization is also a huge field in image processing. There are many applications of skeletonization. You see, the most trivial example that I can find is Kinect. If you see Kinetic, the Xbox sensor, it actually does a kind of skeletonization. I don't think these morphological operators are very good for skeletonizations, but it's good to know that they have also this application. Right, and then to close up, to finish off today's lesson, I promised that I wouldn't talk for more than 1 hour. Let's see about the exercise. So you have this notebook. This is notebook 16. Where we are going to use morphological operators based on they are defined on OpenCV. So there's here we are going to upload the OpenCV figure, and we're going to apply erosion on this figure. Oops, it's not on that figure. I think J is better. Right, this is the result of eroding J. Now I ask you just to play around, change the number of iterations, change the size of the kernel, just so that you get a feel for this erosion. And also let's dilate J, so you get a kind of fatter J, right? Dilate, almost closing up here, right? Now we can add white noise. Add white noise. And we can use, as I said, the morphological operators to clean up noise. It's quite amazing. With black noise, we're going to have to use another one. And just read it through and learn about it. So these are just basic operations, dilation and erosion. And there is now 2 tasks for you to do. Task 22 is to open an image with circles and find the boundary of the circles using morphological erosion. Try with two different disks as structuring elements, one with radius 1 and one with radius 4, and discuss the results of different structuring elements. And just two very simple exercises for you to get a bit of the hang on the application of these morphological operators. All right. So yeah, thank you very much, and I'll see you in the next lesson. Bye.